In the previous video, we saw that moving electric charges can create magnetic fields. Now I'd like to go ahead and get quantitative about that. So let's say, for purposes of discussion, that we have a positive charge. We'll deal with negative charges in a minute here, but let's say we have a positive charge Q here that is moving at some velocity v. And I'm interested in knowing the magnetic field strength and direction at our point of interest right here. The way you get that is through what's called the Biot-Savart Law. So it's not Biot-Savart, it's Biot-Savart. And what you do is you go ahead and you erect a unit vector that points towards your point of interest from the charge. So it's always from the charge towards the point of interest. And we call that unit vector r hat, and it's just right on the way to our point of interest here. The Biot-Savart Law says that the magnetic field vector B will be given by we'll have a couple of constants here. We'll have mu naught over 4 pi. We'll get into those in a moment here. Q V crossed with our r hat over r squared, where r is just plain the distance from the charge to the point of interest. So if we go ahead and do that here, the way I'd like to do it when I take the cross product is I first times the charge and the velocity vector together. So if I have a positive charge, Q times V will point in the same direction as V itself. If it's a negative charge, which we'll get into in a second, Q times V will point in the opposite direction of V itself. And then I take the cross product with r hat. If you prefer, you can take V cross r hat and then times by Q, but keep in mind that if you times by negative charge, you're going to have to flip the answer backwards. So take your pick where you want to do it. But in any event, remembering how we did the right-hand rule, I would be pointing my first finger along the direction Q times V, which since V goes to the right and Q is positive, Q times V will also go to the right. Then my second finger of my right hand will be lined up with r hat. And when you do this, you should get that your thumb is pointing out of the screen. So if this is my point of interest right here, at this location, the magnetic field, due to this moving charge that's located here, moving this way, points out of the screen. Now let's just quickly revisit that for the case of a negative charge. So here I'll go ahead and make the charge negative. Now when you do this, again, remember when you do a cross product with your with the right hand rule that I showed in the previous video, you put the first thing on the first finger, the second thing on the second finger. So here, V still points to the right, but what I'm going to do is I'm going to put Q times V on my index finger. So Q times V will point to the left because this is a negative charge. In fact, let me just draw that in here in gray, just so we're clear on that. So here, Q times V pointed to the right. Here, same magnitude, but opposite direction. Q times V points to the left here because the negative of right is left. So when you do the cross product using your favorite method, if you're doing it the way that I showed in the previous video, you would point your index finger to the left, then you would twist your hand around, your right hand around the index finger until you get your middle finger to match with our hat, and the magnetic field vector at that location will point into the screen. So, as I also said in the previous video, there are a zillion ways to do the right hand rule. If you don't like the way I do it, use whatever your favorite method is. But pause the video and give this a try until you can consistently get the magnetic field in the upper illustration to point out of the screen and in the lower illustration to point into the screen. Okay. So about this constant here, mu naught, its official name is the magnetic permeability of free space, whatever that means. And up until 2019, it was exactly equal to 4 pi times 10 to the negative 7 Tesla meters per ampere. This is no longer exact. But it is really darn close to it. The redefinition of SI units that happened in May of 2019 forced mu naught to no longer be an exact value. It was very carefully chosen so that there would be a 4 pi, so that there would be 2's and pi's to give nice clean cancellations with. But with the redefinition of SI units, mu naught is now forced to be an experimentally obtained value. Experiments have already been done, and the current accepted value is extremely close to this number. So unless you are doing disgustingly precise calculations, which you almost certainly won't be, it's still more than accurate enough to write down 4 pi times 10 to the negative 7 Tesla meters per ampere. So the unit of magnetic field strength is the Tesla. It is named in honor of Nikola Tesla, a Croatian-American physicist and engineer who did all kinds of work on electric motors. You can credit him for AC current, did a lot of work with magnetism, all kinds of cool stuff. Very interesting character. And it is equal to 1 Newton per amp meter. Now, in principle, you can make a magnetic field just by having a single moving charge. But in practice, what you're probably going to do is move a lot of charges. So you're probably going to have a current going down a wire, much like I did with the demonstration of Ørsted's experiment in the previous video. So here, what we're doing is we're imagining we're imagining a segment of wire, and the segment of wire is short enough to be approximately straight. And if it's a finite segment, the current will have to travel some distance delta s, and I'm making this a displacement, so that's why we've got the vector sign here. And the charges are moving at some speed v, the drift velocity in the wire. So we can work out what we already know from what we saw with Oersted's experiment, that above the wire, the magnetic field lines will be in circles, and above the wire, they will be pointing out of the screen, and below the wire, they'll be pointing into the screen if the current is flowing left to right, like it is here. So if I look through this chunk of wire here, we can start with the form of the Biot-Savart Law for a single moving charge. And we can observe here that the drift velocity of the charges has to be equal to delta S over the time it takes them to travel that distance. So if I put that in, that this is delta S over delta T, I will have moved some amount of charge Q in time delta T. So Q over delta T will be a current. And then we will be left with a delta S. So the idea here is QV equals Q times delta S over delta T, which is Q over delta T delta S, which is I delta S, cross R hat over R squared. So our delta S has to point in the same direction as the current, or we're going to have problems. Now usually what we do is we take this all the way to differential form and say that the contribution due to a differential chunk of wire will be mu naught over 4 pi I ds cross R hat over R squared. So let's just double check that this does indeed give us what we want. So again, let's go and say that this is my point of interest right here. I would go ahead and drop in an R hat pointing towards here. So I is always going to be positive because it's conventional current, and delta S will always point, or ds will always point in the direction of the flow of conventional current. So let's follow this through. Put your index finger on the along the conventional current, rotate your hand to get your middle finger to point to R hat, and sure enough, it actually, sure enough, the contribution to the magnetic field at that location points out of the screen. And you can do this at literally for every chunk along the wire, and they will all contribute the same. And since the problem is rotationally symmetric, this means that the magnetic field lines we generate do indeed have to be circles. Now, before we dive in further, I just want to point out that sometimes books write the Biot-Savart Law slightly differently than the way I've written it here. So I'll just note what they sometimes do. I think this is one of those things where they're being too cute for their own good. You can write a vector R as opposed to the unit vector R hat that points at the point of interest. You can draw a vector R that points all the way from the charge to the point of interest. And when they do that, they write mu naught over 4 pi QV cross R over R cubed. Now, where the heck did this extra R cubed come from? That comes from the fact that a way to make this unit vector R hat, is to take this vector R here that points the way you want it to go, and then divide by its length, because remember, a unit vector is literally the number 1 that goes where you want it to go. So you can take this R vector here and divide it by its magnitude r, and that gives you r hat, which gives you this cross r over r cubed. These are the same, but I'm not a fan of writing it this way that I've got here in gray. I'm a bigger fan of writing it this way, and the reason is that I think it makes it clearer that the Biot-Savart Law is an inverse square law. The strength of the magnetic field due to a moving charge falls off as the square of the distance you are from that moving charge. That's less obvious here, so I'm less of a fan of writing it this way, but there are plenty of books that do. So if in some future reading you run across it in this form, it's exactly the same thing as this, and you're just supposed to recognize that one of these r's exists to make this r an r hat. All right, so let's go ahead and figure out the magnetic field strength of a long straight wire. So let's say we carry some current I, like so, and I want to know the magnetic field strength some distance r away from the wire here. So first off, we can already figure out the direction of the magnetic field because we know that for a long wire, if we put our thumb along the direction of the conventional current, the magnetic field lines have to be circles that go around the wire in the plane perpendicular to the wire. And if we follow the curl of the fingers of our right hand, at this location right here, they go into the screen. At the symmetric location over here, it would be going out of the screen. Behind the wire, it would be going to the left, and in front of the wire, it would be going to the right. So what we'll do, and let's just say that we are some distance r away from the wire. What we'll do is we will look at a typical chunk of current, typical chunk of wire here, carrying current, ds, and again, we point this differential chunk in the same direction as the conventional current. So my unit vector r hat is going to point towards the point of interest here. And we will say that this distance here is r, like so. And the natural coordinate system that we will want to draw will have the origin going through the plane that contains the origin going through the point of interest. And we'll just call this distance here s, since I've already been using ds there. All right. And then I guess for completeness sake, let's go ahead and label this angle right here. That angle is phi. So we start by writing the Biot-Savart Law, and that will say dB is equal to mu naught over 4 pi I ds cross r hat over r squared. Now, we already got the direction of the magnetic field. We know that at the end, when we add up all the dBs here, B has to point into the screen at this location. So when we get the magnitude, so when we evaluate the cross product for magnitude, we'll be writing dB equals mu naught over 4 pi I. Now, when we evaluate the cross product, you're going to take this thing here, ds, you're going to times it by this. Now the magnitude of this is just 1. And then you multiply by the sine of the angle in between them. And we'll divide by r squared. Okay. Now we need to figure out how to express our phi in terms of S and R here. And actually, we ultimately want to depend on big R. So we'll observe that this distance, little r here, is equal to the square root of s squared plus r squared. So then we can observe that the sine of phi will be equal to, well, this angle is phi, and technically this angle here is the supplement of phi. But if we remember our trig identities, the sine of the supplement is equal to the sine of the sine. So the sine of this angle is the same as the sine of this angle. So that will be from SOHCAHTOA, that will be the opposite, which is r, over the hypotenuse, which is root s squared plus r squared. So, okay, we can go ahead and make our substitutions here. So that gives us that dB is equal to mu naught over 4 pi. And all of this is just going to give me an I, and then I've got this sine phi here, which is going to give me an R. And then r squared here is this root squared. And that'll be times by another one of those from the sine. So this will give me ds over s squared plus r squared to the 3/2 power. Okay. So now we can go ahead, pull out the constants and integrate. So b will be equal to mu naught over 4 pi I r. And we'll integrate, since it's a long straight wire, from minus infinity to infinity, ds over s squared plus r squared to the 3/2 power. And this is another one of those integrals that's a little easier to do if you fold it. So we're going to pick up a 2 here from folding the integral over 4 pi I r. And this will be the integral from 0 to infinity ds over s squared plus r squared to the 3/2. And this is because this the integral is symmetric. You get the same answer regardless of whether s is positive or negative. Okay, so this is why you have the 4 pi's and stuff that cancels nicely there. And this integral is eminently lookable upable. And when you look it up, you will have mu naught over 2 pi now. 2 pi I r s over r squared times the square root of s squared plus r squared, evaluated from 0 to infinity. When you put in 0, the limit 0, that's the easier one to do. You'll have a 0 in the numerator, but in the denominator, this is 0, but that's not 0, so the denominator is not 0, so you're all good there. For the infinity bit, you're going to get infinity over infinity. which means you're going to have to apply L'Hopital's rule. And when you do apply L'Hopital's rule, you will get that the magnetic field strength is mu naught I over 2 pi r. So just to give some sense of scale here, for basically how big of a unit the Tesla is, let's say you have a wire carrying 10 amps. And let's say you are a centimeter away from the wire. The magnetic field strength due to that current will be equal to mu naught over 2 pi I over r. Mu naught is 4 pi times 10 to the negative 7 Tesla meters per amp over 2 pi. We're going to say 10 amps and divide by 0.01 meters. So the pi's will cancel, and we'll be left with 2 times 10 to the negative 7. Now, when I multiply by 10, that'll make that 10 to the negative 6. When I divide by 10 to the negative 2, that will make that 10 to the negative 4. So we get 2 times 10 to the negative 4 Teslas, or this works out to be 0.2 milliteslas. Now, 10 amps is an awful lot of current. You're going to have to gauge, it's not going to be a fire hose of a wire, but, it's a noticeable thickness of wire. And it's certainly not the thickness that's going into your USB cables or anything like that. Certainly a lot thicker than that. And a centimeter is fairly close to the wire. So you can see why I was mentioning that I was having to carry a lot of current in order to do an effective demonstration. Now, a Tesla is an awful lot of magnetic field strength. There are electromagnets out there that will make magnetic field strengths that are, say, up to a few Teslas. For instance, in MRI machines, those are like integer numbers of Teslas. And already you're at a point where you have to make sure to remove all jewelry. You have to wear special clothes that don't have any metal in them and all of that. For comparison, the Earth's magnetic field is about 50 microteslas if you're near the surface of the Earth. And while this may have been passed, to my knowledge, basically about the biggest, baddest electromagnet I'm aware of that anyone has ever made was a superconducting magnet that was so large that when it was transported, they had to use 48 axles on the between 40 and 48 axles, depending on the state it was being moved through at the time. And even then, that the load was far exceeding the normal road weight limit for an axle. It was a very large, basically you need to build a building around it kind of magnet, and that made a magnetic field strength of 20 Teslas. So Tesla strength fields are not impossible, but the Tesla is a very large unit of magnetic field strength, much like a farad capacitor is possible, but it's on the bigger side. Teslas are the same kind of way. Okay. So in the next video, we'll do a few more applications of the Biot-Savart Law, and then we'll take it from there. Have a good one.